Okay, cool. I think everybody already knows Chao. Chao is my fourth year PhD student. He joined us from University of Michigan before, and he's spending 4 years in my group studying this topic of spatial representation for embodied intelligence. Um, I think the committee member has already heard his proposal, so knows part of his work before, and he just recently was able to complete his entire thesis. Without further ado, I think Chao, the floor is yours.
Okay. Yeah. Okay. All right. Hello. My name is Chao Chen, a PhD student at AI Force Lab. So today I'll present my PhD thesis, entitled "Topological and Metric Spatial Representation for Embodied Agents." This work explores how the embodied agents, like mobile robot, can understand and navigate the world using two complementary map types, like topological maps and also metric maps. I'll walk through how we designed this learning system to build and use this map effectively. Okay, so quick recap about myself. I hold two master degrees from USC and UMich, and now I'm a PhD student, PhD candidate at NYU in computer science department. So my background spans both the research and engineer with hands-on experience at IHMC for robotics and also Robert Bosch for autonomous driving, as well as a teaching assistant and a project leadership experiences. So I have had multiple project works listed during my PhD, and today I will mainly focus on three of them, and two about like topological mapping, and one is about metric mapping. So today I'll also cover several key topics, including the background, the role of mapping in body AI, metric versus topological mapping, challenges in topological reasoning when the visual overlap is actually low, and also my future directions and acknowledgements. So first, background overview. So let's start with the background of the mapping in body AI, including the importance, history, pros and cons. Embodied AI is rapidly advancing in perception, localization, and also planning. And mapping is actually the fundamental to all of the three. So in this talk, I'll mainly focus on the two key mapping representations in embodied AI, topological and also metric. So this is actually the mapping evolutions in embodied AI through the 5 key stages. So first came on the hand drawing maps. This is simple but effective. And then the grid maps involves more structured navigations. In the later stage, in 2000s, with better sensors, metric maps then capture the precise details, boosting the accuracy. Next, topological map follows adding the semantic relationship beyond distances. Now we have the modern approaches combines both types using the tools like visual odometries or place recognitions for richer maps. Now let's look at different utilities of these two type of maps, metric map and also topological maps. So for metric maps are precise and ideal for the accurate environment representation, but they are actually computationally expensive, best for close range, also high precision planning. For topological maps, treat the precision for efficiency and also scalability, making them suitable for large scale or long range planning where the structure matters more than the details. So each map serves a different serve different needs depending on the system's requirements. We come to our first mapping type, metric mapping. So metric mappings capture the precise geometric details of the environment, making it ideal for high precision planning, localization, and collision avoidance. It can be categorized into two main types. I call it like real-time mapping, which continuously updates as the environment is navigated and is well explored for this area. The second part is called offline map optimization, which refines out and optimize the map post data collection for maximum accuracy and also usability. So today we'll only mainly discuss on the offline map optimization, focusing on the self-supervised approach called deep mapping. So deep mapping registers multiple point clouds to a global reference using a learnable post network, allowing for alignment from random initialization. This makes it like a powerful tool for building unified environment maps from several separated scans. However, deep mapping is even the deep mapping is innovative, it still struggle with scalability and limited to a small environment. This is due to several main key factors. The first is actually lack of loop closure, so the drift accumulates without correction. Second is local registration is fragile, relying heavily on the paraposes, so single failures can break the entire mapping, as shown here. Third, it converges slowly, limiting the efficiency in real-world scenarios. So to overcome deep mapping's limitations, we aim to extend its use to large-scale environments like city level or campus level. So we actually apply the multiple point cloud registration. This is like solving a jigsaw puzzle. Each scan is a piece, and the goal is to align them seamlessly into a complete map. Deep mapping tool is aimed to solve like a more complete, complex structure. Solving large piece puzzles inspire our approach to point cloud mapping. In deep mapping 2, we apply 3 techniques. First, grouping geographically adjacent frame. This is like sorting the puzzles piece by piece by proximity and to preserve the spatial coherence. Second, to optimize this group together. This is like assembling small pieces section together, and this is to reduce the error accumulation. Third, to ensure the accurate local registration. This is just like putting each puzzle piece must to fit precisely. Local alignment ensures the global map quality. Building on these ideas, our work, the mapping tool, which is a self-supervised point cloud registration method, is designed to overcome the limitation of our earlier method. First, we improve the frame grouping. Earlier method like deep mapping, grouping the frames randomly or temporarily, which fails due to even like single batch frame registration. To address this, we propose a spatial neighbor-based grouping, which cluster frames based on the geographical proximity. We use virtual place recognition to find the spatial neighbors to build a spatial topology map as a structural prior to guide the mapping tool. This makes mapping become more robust and accurate, especially at large scales. Next, we optimize those adjacent frames together. Instead of processing the frames independently, we group the spatial neighbors in the same batch, so which improve the local alignment and also the map consistency. We also add a consistency loss to penalize the misalignment neighbors, encouraging the accurate registration. Visual result shows clearly here. On the left, the good alignment lead to a smooth map. A pool grouping basically causes a visible artifact. Here, the workflow for optimizing the alignment of adjacency frames. We start with the paraposes from existing method to get the initial frame positions like ICP or legal norm. Then in the pre-processing stage, we perform 2 key steps. First is called batch construction. So group those frames based on their geographic proximity. I will tell later how to do this. And the second is actually the pairwise transformation estimation to compute the relative transform between each within each batch using the method like ICP or FTR. During the training below, we basically follow the same procedure as the mapping structure, but adding a consistency loss to penalize the misalignment within each batch, ensuring accurate and local registration. So during optimization, we pick one frame as an anchor. Within each batch, we include in the single anchor frame A and its neighbors frames N. So we transform the neighbor point cloud to the anchor frames using the pre-computed relative pose from ICP and FTR as discussed, and then creating a multiple version of that same anchor. Then to align multiple versions of the anchors, we use an L2 losses to penalize the difference between each version and enforcing the local consistency and the precise alignment. To evaluate deep mapping 2, we compare absolute trajectory error, ATE, on the KT and also NCLT datasets. The figure shows the TATE, which is translational ATE, those error measured in meters on the top, and also the rotational ATE, RATE, measured in degree, shows on the bottom. We observed two key points. So basically, deep mapping 2 performed the best when initializing with the prior poses for ICP and a legal norm. Second is the quality of the initial pose directly impacts the optimization process. Legal norm initialization basically lead a better result than the ICP initialization. So in summary, deep mapping 2 achieved the high accuracy, effectively correct drift, converge faster than the original deep mapping. However, it still relies on the good priors, so making the initial construction essential for large-scale mapping. Next, let's look at some ablation studies to understand how the impact of each component in deep mapping 2 works. Here are the results for original deep mapping. And first, the batch organizations basically group the spatial adjacency frames, introduce some implicit loop closure, which helps to correct those drift, correct the drifts, especially in large-scale environment with frequent revisit. Second, the consistency loss here is not only improve the mapping quality, but also it speed up the convergence, making the optimization become more efficient. Finally, by combining both leads to the best result. This component work together to boost both accuracy and also efficiency. To summarize this work, batch organization helped to correct the drift by implicitly introducing the loop closure, critical for accurate large-scale mapping. The consistency loss further improved the local registration and speed up the convergence, making the optimization faster and become more reliable. Then next, let's talk about how to build these batches. We use in vitro place recognitions to identify those spatial neighbors and construct the spatial topology maps. Since deep mapping 2 is fully self-supervised, so building these maps without any manual labels remains a key challenges. Next, let's turn our attention to topological mapping and reasoning. As mentioned, topological maps are well suited for long-range planning. So nodes represent the key regions, not exactly geometry, while the edges capture the spatial relationship, like proximity or accessibility. In our SLAM setup, edges simply specifically indicate the spatial closeness between the nodes, enable effective reasoning and navigation. Topological maps offers efficient and scalable solutions, especially for loop closure, long-range planning, and topological reasoning. They help the system to recognize, revisit places, correct drift, and plan over a large distance without relying on the detailed metric data. Because they are lightweighted, so they are computationally efficient, ideal for large-scale or resource-limited settings. However, those challenges still remains. First, selecting the meaningful keynote is difficult. Inaccurate relationship between the nodes can hurt the map quality. Third, and topology maps may struggle with complex decisions needing high precision. Overall, topological tasks can fall into these two main categories. First, topological mapping, used in SLAM and to find the key locations and their spatial relationship for real-time localization. Connecting nodes are usually close in space. Second, topological reasoning, which is useful when the image pairs share the few features and it connects nodes based on the visual similarities, not just like the spatial proximity capturing border relationship. Next, I will introduce my work on topology mapping, TF-VPR, which is a self-supervised place recognition method by refining temporal and feature to-do labels from panoramic data, which has been accepted ICRA IL 2025 this year. So the motivation behind TF-VPR addresses the task involved two primary nodes, auto-labeling and generalization. Auto-labeling in TF-VPR aims to generate a binary topology graph based on the set of nodes, where we're using the same data set for training and testing. The goal here is to use the network itself to overfit the data set and serve as topology map annotator. In generalization mode, we evaluate how well the model can predict the new unseen data set beyond what had been trained on. In this work, we mainly focus on the dataset where the training dataset and also test set are quite similar, like a model that I've trained to recognize the places inside a similar room with a similar furniture and lighting. Let's make some definition of the query and true, false, positive. So a query is images of the data captured at specific location by a camera and sensors. The goal of virtual place recognition, VPR, is to find the spatial neighbors where the location is close to that query. True positive are correctly retrieved neighbors nearby, and where the false positive are incorrect matches. So my next research question here is, how do we get the spatial positive in a self-supervised way? My answer to this question is by combining temporal and feature information. That is, the spatial positive is equal to temporal positive plus feature positive. Let's recap some definitions of the positive here. Temporal positive are the frames close in time. Feature positive are the frames close in VPR features. Spatial positive they are physically close to each other. So next, let's talk about TF-VPR pipeline. It consists of like 4 main steps: labeling, training, expansion, and contraction. The first step is called initial labeling. To construct the triplet for training based on their time sequences, those captures close in time are labeled as positive, while the others are called temporal negatives. Next is training. We're using the NetVilla style model with triplet loss to distinguish the positive and negatives. To improve the robustness, we augment the data by rotating the point cloud horizontally or rolling the panoramic images, thus simulating the different viewpoint change. And next, we do the expansion. For each query frames, we look at the feature distance to find more potential positives. By comparing those features, we discover additional frames that are likely nearby neighbors. However, there are still some potential false positive there. So the next is called contraction. We're using geometric verification method to remove those false positive by checking the spatial consistency. This is clears up the positive and negative set, basically making the training become more accurate and also effective. The next step is called next epoch labeling. We update the frame labeling using the cleaned positive and negatives from geometric verification. This way, the model is trained on the accurate data in the next round, improving the performance overall. To evaluate the model's ability to retrieve the positive from different directions, we introduce a metric called heading diversity. We track the heading variations. The figure shows that we have 360-degree spaces is actually divided into 8 bins. To avoid those trivial cases, we exclude those 2 bins close to the query. And also the metric then compute the proportion of the remaining bins that are covered by correct retrievals. In this example, we found that 5/6 of the bins are correctly covered. That in this case, the range between 270 to 175 degree, this bin is actually missed. For auto-labeling performance, the plots compare the baseline result ablations experiment. Among the baselines, SPTM is a self-supervised method that relies solely on the temporal information without any data augmentations or label update, keeping the labels fixed throughout the training. The evaluation metrics, including heading diversity HD, recall at 1, 5, 10. We evaluate on 2 data sets. On the left is actually Kitty data set, a real-world outdoor point cloud data set. On the right is actually habitat data set. This is like an indoor simulated RGB data set. So for Kitty data set, so SPTM with feature expansion and also the contraction, highlight as SPTM plus F, showing in green on the left, perform the best. Since the Kitty involves constrained movement along the road, which is like turn left, go straight, or turn right. The movement is actually restricted. So data augmentation has little impact. For habitat, SPTM with both augmentation, feature expansion and contraction, labeled as SPTM plus A plus F, showing in green, shows on the right, achieve the best result overall. Here we show the augmentation basically help significantly due to less constraint and movement and will become more open in indoor environment. In the generalization experiment, SPTM with augmentation of feature expansion contraction, SPTM plus A plus F achieved the best performance, outperforming all other baselines. Remarkably, it even surpassed the supervised model when there was like large domain gap between the training and test set. This result indicates VPR performed best when the domain gap is small, but its ability to generalize well to new unseen environment without labeled data training set is especially valuable. This makes TF-VPR become highly practical for real-world scenario where the label data may be limited or even unavailable, enable effective place recognitions across diverse settings. Yeah, sure.
What's the network? So if you got a network and what was it pre-trained on?
Oh,
Is it from scratch?
Yeah, normally everything is actually pre-trained from scratch.
Okay.
Yeah.
And then I'm sorry you may have said it, but what was the architecture?
You mean this architecture?
Yeah, that you're using.
So for TF-VPR, the architecture is just follow exactly the same net VLAN. So net VLAN is using the ResNet encoder, and then just try to use the triplet loss.
Neat.
Okay, so next, let's discuss the top-end retrieval visualization. TF-VPR outperformed the other baselines, demonstrating its strong capability in accurately retrieving the correct retrieval, so positives. Next, here we have some per frame heading diversity visualization. Is the color coded showing the heading diversity value from 0 to 1, comparing the method like SPTM, TF-VPR, and also overfitting supervised baseline. So TF-VPR stands out by retrieving positive across a wider range of headings, showing it captures diverse spatial relations well. So in summary, so this work contributes 3 key points. Effective supervised VPR without actual annotation. Second is this robust retrieval of spatial positive from diverse heading. Third is the introduction of the heading diversity metric to evaluate and visualize the retrieval across multiple directions. Okay. Now let's look at the final part, which is let's discuss the topological reasoning, which is go beyond traditional SLAM topology maps. Like unlike the SLAM's focus on spatial navigation, topological reasoning analyze the complex relationship between the image pair or nodes, even with some minimal shared visual features. Next, I will introduce my work on topological reasoning covision, which focus on covisibility reasoning on sparse indoor set. We leverage shared visible regions between the images to understand spatial relationship in the sparse environment. This work is actually received by ICCV workshop. So topological reasoning aims to understand how the spaces are connected, not their exact shapes or locations. It helps the agent to infer the environment structure, like the pathway or intersection, even without direct visual cues. Unlike this typical image analysis, it focuses on the spatial graph, supporting the high-level planning based on the connectivity instead of the geometry. As we discussed last time, we start with a quick example. Given these 2 images, do you think they are spatially connected? So they belong to the same environment linked by a path? So as said before, they belong to the same environment although they look different at the beginning, but a top-down view show the spatial connections. So co-visibility reasoning estimates spatial adjacency by identifying shared visible regions between images, even when the overlap is limited. Unlike the feature-based method, it focuses common visibility to infer a spatial structure. It's difficult depending on its overlapping level. I categorize into three types: easy, medium, hard. Easy when we have large overlap, straightforward adjacency. This is easy trivial case. And the second is medium. Medium have partial overlap. It needs a deeper analysis. For the harder case, it have minimum overlap, is challenging without actual context. So in sparse indoor data set, co-visible regions are rare, and also existing method normally fails on the harder cases. Later, I will do some failure mode analysis based on these difficulty levels. In this work, we basically provide two potential solutions. First is actually multi-view method. Second is actually VLM reasoning method. So next, before we go into the method itself, data generation for the co-visibility reasoning is important. To address this task, we first using a sparse set of images that cover the full thing. We're using some like rule-based method, greedy strategy to select the images to both explore the new areas and also stay well connected to the existing topology. This ensured the border coverage while preserving the spatial coherence. We're using two data set, Gibson, also the larger scale data set called HM3D. We evaluated some several baselines for naive baseline like feature matching, binary classification, contrast learning method to improve the baseline to some improved baselines like 3D reconstruction, VLM method for complex image pairs. To further improve the pairwise reasoning, we also propose using some multiple surrounding images, to offer some diverse viewpoint and strengthen the robustness and accuracy. For evaluations, we're using the graph IOU, which measures how well the predicted connected graph matches the ground truth graph. The second is the AUC of the graph IOU versus the threshold, which reflect the model stability across different decision boundaries. Next, we also introduced our own mask multi-view pipeline CoVis. So before CoVis, from our initial experience, the multi-view 3D method, like a multi-view duster, performs well, supporting the idea that multi-view inputs help with the pairwise reasoning. So we built our first version, is called CoVis V1. Based on that insight, it's just like building on top of the multi-view duster encoder decoder backbone. We simply replace its original head with a classification head to predict the co-visibility instead of reconstructing the environment. The encoder basically extract the initial feature from each of the view, and then the decoder exchange the different views information layer by layer. At each layer, we pick one view as the reference token and perform the cross attention with all the other views. In the next layer, we switch to the different view as reference, and this layer by layer attentions basically let the model gradually integrate the information across all the views. So the decoder outputs then go through some MLP layers, then finally feed into a classification head. When we use some cross attention across all the views, including the reference, positive and negatives, we are forcing the reference and positive to exchange the information with the negative, because the decoder. This negative is kind of irrelevant to those positive and reference. This basically contaminates their features, since most of the negatives views do not share any meaningful content with the reference or positives. Here is one example, like the model's attentions on the positive does not focus on the co-visible region, which it should be focusing on. This happens because of feature contamination, as I mentioned earlier, where the unrelated negative interfere with the reference and positive pairs. So this is what should looks like. The attention should looks like. Basically, the attention should focus somehow on the actual co-visible regions. Here's our refined pipeline. After the MLP, we got a pixel-wise feature map, and we're using a mask hat to predict a binary mask. Next, we apply this pixel-wise dot product between the mask and also the original noisy attention map to filter those unrelated features. So which gives the cleaned up attention map like we showed earlier on the lower right. With the help of the mask predictions, we arrive at our final mask multiple view pipeline COVIS. To further elaborate how those on the effectiveness of the masking, we actually show a few visualization and also ablation studies. First, a visualization on the left, we show a mask example, including the ground truth mask, its corresponding binarized mask, and our predicted binarized mask. This visualizes how our model learns to focus on the overlapping areas between the views. Then, ablation shows on the right, we compare different masking strategy. First, without any mask, feature fusions become very noisy and less accurate. The performance is not that good. So with ground truth mask, giving the best performance, validating the importance of the co-visibility guidance. Supervising the mask using with increasing noise, basically showing that the performance gradually decrease, demonstrating the system sensitivity to mask quality. This result highlights the critical role of accurate co-visibility masking in multi-view reasoning. Let's look at some visualization across all the methods. So first, we examine some naive baselines showing in gray, which cover those traditional method, like matching method, like traditional matching method, contrasting learning method, and also the pairwise classification method. The performance overall is not that promising. Second, let's look at the middle portion and also the right portion. This is actually the improved method and also the highlight top performers. This including those VRM-based method, 3D reconstruction approaches, and also our mass multi-view pipeline, COVIS. Basically, the top performers, including the pairwise and also multi-view GPT-4o method, as well as the COVIS method. Interestingly, the multi-view GPT-4o performed worse than the pairwise GPT-4o, suggesting that prompting GPT-4o with a multiple view is still challenging. Note that not all the VLM method works. Other VLM methods listed here tend to perform worse and less consistently. Besides, for COVIS, using the pre-trained encoder with a fine-tuned classification hat basically achieved a better result than training everything from scratch, highlighting the benefit of leveraging some pre-trained features in the mask multi-view pipeline COVIS. As mentioned earlier, we further analysis COVIS performance under different level of difficulties throughout the detailed failure model analysis. We examine two key dimensions, image overlap, which reflect the edge level sparsity, how much two images share the visible regions. Second is called scene sparsity, which reflect the graphic level sparsity, with how densely they are connected to the entire co-visibility graph is. So these two axes reveal how the performance degrades under the increasing structural complexity, both at the pairwise level and also the global wise scene level. In this analysis, we can conclude that GPT-4o outperform all the other VLM methods. Both COVIS and also GPT-4o achieved the most significant improvement over all the baselines in the hard case scenarios. This hard case scenario basically highlight that the limited viewpoints of the overlap and the scene sparsity are the primary source of difficulty.
So can I maybe the graph is including what's the definition of sparsity? I thought graph is the scene graph is more like a scene topology, right? What's the difference between sparsity and topology?
Sparsity and topology.
Usually the graph connects, okay, this object connects to that object as represented by this. Is it a scene graph in the first place? Oh.
Yeah, you should explain this.
Oh, okay.
What is this graph?
Okay, so
the node and
so basically the edge level is just consider this a pair of the images, right? But the scene level, basically, I compute the sum of those how to say, the overlapping of all edges, the sum of the
What
overlapping
is an edge?
edge.
What is a node?
Yeah, you need to explain this.
Oh,
What is a
actually.
node?
You
What
need to
is an
explain
edge?
this whole
So-
graph.
sorry
You
about
have to
that.
explain that.
Oh yeah, sorry. Node is just like the image taken in the scene. The edge is actually the human reasoned. If these two nodes are connected in the same, it means if you believe these two images belong to the same thing, or there are paths between there's a path between one images to another images.
Visibility.
It's just a co-visibility.
It's a visibility now.
Yeah.
So,
So
co-
a node is an image. A
Yeah,
node
yeah.
is an image.
and the solid edge means they are from the same object. The dashed, mean
Oh,
I actually don't know what's the.
sorry, the solid means because I just try to distinguish the edge level. Yeah,
okay.
actually, this graph is a little bit misleading.
Yeah.
I was just trying to say the solid just means I'm only concentrating on edge level, but the sparsity means I consider this whole thing as the thing as a whole. Basically, I compute
so-
the average.
Okay.
Yeah, so for Chi's question, I think the edge means if any two nodes are connected by an
Yeah.
edge, forget about the dash
Yeah.
and solid. So any two nodes that are connected by an edge means these two nodes, the image of these two nodes are observing something in common.
Yeah, yeah. It's
Yeah.
just from different views, different.
Yeah.
Mhm.
That's the co-visibility.
Okay, so the edge level is the edge in this graph.
Mm.
So now, oh yeah,
Right.
yeah,
Yeah.
for your first.
Okay. So next, let's look at two key application of the covisions. Since the first is just scene reconstruction. So the 3D reconstruction aims to build a 3D environment from a set of images. However, reconstructing from all the images at once is time consuming and also inefficient. A smarter approach is to reconstruct only frames that share some common views of the images like co-visible peers. Using such method that reduce the memory and also computations while maintaining the accuracy. So this requires a topology map to identify which frames are co-visible to each other. Then doing the reconstruction based on this topology, co-visible topology. On the right, we show some 3D reconstruction result using different graphs. We have a star-shaped graph, and also we have a co-vis predicted graph, and also we have the ground truth topology annotated by human. We can see that the reconstruction from the co-vis map and also the ground truth map are very similar to each other. And here we show some quantitative result. Using the covision graph to select the neighbors achieve a stronger balance. Its accuracy is very close to the ground truth and also complete map, but with significant lower memory and the runtime cost. A second application is auto-labeling. So our co-visible graph helps automatically to generate the training pairs for tasks like VPR or cross-view completion. For example, in cross-view completion, we need the image pair with shared views. This can be obtained, or this can be done by selecting the pairs that are connected in the graph, indicating the shared co-visibility. We compare the completions on testings using model trained on sparse versus some dense co-visibility graph. Even with fewer connections, the sparse graph yields a stronger result, showing that the model generalizes well from the fewer but meaningful pairs. And surprisingly, with the sparse graph, like a sparse co-visibility graph, despite having fewer edges, it performs slightly better than the dense graph for generating the training triplet.
The PSNR of the graph.
What?
What's the PSNR of the graph?
We're just doing some quality. I mean, this is a PSNR for reconstruct. So it's for the reconstruction. Yeah.
For the cross-view completion task.
Task
Oh,
for this
for
task.
this task.
Yeah.
Okay,
Yeah.
okay.
He's using this to show that this co-visibility reasoning
Yeah.
is helping that task.
Yeah.
Absolutely.
Okay, so to summarize, we introduce a new vision task, co-visibility reasoning, which focus on understanding spatial adjacency from image pairs. Also, we built on a benchmark with a wider range of baselines, including human performance, and we propose CoVis, a mask multi-view pipeline that effectively handles this task by leveraging the structured queues across multiple views. Let's move to the conclusion section. In the conclusion, our work bridged the two significant mapping, metric mapping, topology mapping. For topology mapping, we distinguish with two primary directions, a classic like topology mapping for SLAM, focusing on supporting the navigations and also the localization tasks. And also second is topology reasoning, a more advanced directions where the reasoning about co-visibility and also spatial relationship allows us to explore challenging scenarios with the minimum overlap or distinct features. In summary, we developed the mapping tool for precise pose optimizations in mapping in metric mapping, TF-VPR for scalable SLAM-based topology mapping method, and also CoVision for advanced topology reasoning in challenging sparse dataset. So my dissertation focused on embodied AI with mapping, addressing these three key categories: metric mapping, topology mapping, and also the topology reasoning. This key three type of mapping balancing the robustness, efficiency, and also scalability. Various mapping methods serve for different purposes, each addressing unique challenges in embodied AI. Here is a list of work I have completed during my PhD, and 2 more work has been accepted by ICC workshop after last round of PhD proposal. So next, let's quickly go through some concurrent works and unfinished projects. So this including the advancement in metric mapping and also their applications in downstream tasks such as planning. To be more specific, for metric mapping, I'm working on at OCC, which is a hybrid resolution occupancy prediction method model aimed to enhancing the precisions of the metric mapping. It's now pending for resubmission to a conference. Finally, for planning, I'm focusing on parking with uncertainty project, which combines with the mapping with planning specific for parking scenario. The goal is to ensure the mapping and also the planning supported with each other to improve the real-time decision making making in the complicated environment like parking environment. This work is actually on the final stage of like paper drafting stage. So lastly, I would like to acknowledge everyone who helped me and actually contributed my work. First, my advisor and collaborators for their guidance and valuable insight throughout my research, their expertise and insights that helped me to key roles in shaping my work. I also would like to express my gratitude to my colleagues at Bosch, where I had the opportunity to apply my research in the practical settings. This experience simply gained was crucial in bridging the gap between the theory and application. I would also like to extend my fulfilled thanks to the lab mate at AI Force. Their consistent collaboration and feedback have made me had made this journal become more like enjoyable and productive. And also including also my committee members inside my thesis and also my wife and my babies. Yeah. Thank you for your attention. If you have any questions, feel free to ask now. For further inquiries, you can reach me via the emails or visit my personal webpage. I'm happy to discuss anything further after this presentation. Thank you.
Well, thanks, Chao, for the presentation. So the procedure, I guess, is we have 2 like members not in the committee attending this defense. So if you have any questions, this is your chance to ask Chao. So we have 1 person in the room and 1 person online.
Yeah.
So do you have any question for? Okay. Hammond, do you have any question for Chao?
No, I don't have any question for Chao, but Chao, really good presentation.
Thank you. Thank you, Helen.
Great.
All right, see you guys.
Thank you. So the next step is to let me stop recording first.